Resistive plate chambers working at high rate. Introduction. Resistive plate chambers, often referred to as RPCs, have been in use for a long time in low-rate experiments with gas gains around 10 to the power of 8. In this operational mode, the charge of the signals induced on the pickup strips is around 100 picocoulombs, which limits the maximum rate at which the detector can efficiently operate to values around 100 Hz per square centimeter. Recent proposals have suggested the use of RPCs for constructing large area triggers for the ATLAS and CMS detectors at the Large Hadron Collider, or LHC, due to their excellent time resolution and low cost. Monte Carlo calculations have indicated that the secondary interactions of high-energy particles with the detectors and accelerator elements result in a severe radiation background. Thus, improving the RPC's rate capability was essential for their use in LHC experiments. Experimental layout. The RPCs tested in this study were single-gap chambers with a double readout, as illustrated in Figure 1. These chambers were constructed with bakelite plates possessing a volume resistivity of approximately 0.5 by 10 to the power of 11 ohm centimeters, with dimensions of 50 by 50 centimeters and a thickness of 2 millimeters. The results presented here are related to the RD5 runs conducted in August 1994 with high-intensity pion beams. These results are specific to the chamber equipped with the higher front-end amplification. A gas mixture of butane and freon CF3Br was used in varying percentages, from 50% to 85% freon. The behavior of the RPC efficiency as a function of the high voltage is shown in Figure 3. At different beam fluxes and for a gas mixture of 60% freon and 40% butane, the plateau efficiency is achieved at higher voltages for higher rates, since it is necessary to compensate for the reduction of the electric field in the gas due to charge flow through the resistive plates. The rate capability of the chamber is demonstrated in Figure 4. The detector was filled with a mixture of 85% freon and 15% butane. Up to 1 kilohertz per square centimeter, the efficiency is about 97%, but it starts to decrease at 10 kilohertz per square centimeter, where it drops to 65%. The quoted beam fluxes are average values measured using the multi-wire chambers inside the beam spot and do not include the counting rate induced by the cobalt source. The rate at the beam spot position was about 150 Hz per square centimeter, with the RPC sensitivity to low-energy photons being around 10 to the power of -2. Figure 5 presents the time resolution as a function of the beam flux. The time resolution, defined as the root mean square, RMS, width of a Gaussian fit to the time distribution, is 1.1 nanoseconds up to a beam flux of 1 kilohertz per square centimeter, and then starts to degrade, reaching 2 nanoseconds at a beam flux of 10 kilohertz per square centimeter. The quoted resolutions include a significant contribution of 0.9 nanoseconds due to the trigger scintillator jitter. The distribution of the time delay of the chamber signals relative to the beam trigger scintillators versus the beam flux is shown in Figure 6. The delay increases by only 1 nanosecond when the flux ranges between 0.4 and 1 kilohertz per square centimeter, which marks a considerable improvement due to the high gas gain operation mode. Finally, the total charge collected on the pickup strips is depicted in Figure 7 for a gas mixture of 60% freon and 40% butane, and in Figure 8 for 85% freon and 15% butane. The beam flux was 450 Hz per square centimeter. A strip was contributing to the sum only if its charge exceeded 3 times the RMS of its pedestal. Taking into account the front-end amplification, the estimated input charge at the operating voltage, giving full efficiency, is approximately 1 picocoulomb for the mixture of 60% freon and 40% butane, and about 0.5 picocoulombs for 85% freon and 15% butane. Conclusions. The researchers have tested resistive plate chambers, RPCs, with double-sided strip readout operating at low gas gain under continuous and uniform irradiation of a photon source that simulates the background conditions expected at the Large Hadron Collider, LHC. The team measured a rate capability of 97% efficiency at 1 kilohertz per square centimeter and a time resolution of 1.1 nanoseconds up to a beam flux of 1 kilohertz per square centimeter, which is largely adequate for the LHC background conditions. The total charge seen by the detector was approximately 0.5 picocoulombs for a gas mixture of 85% freon and 15% butane, and increases for mixtures with higher freon content. These results suggest that RPCs are fully suitable for the muon trigger systems of the ATLAS and CMS experiments at LHC.